Good morning, everyone, and welcome to the Yvonne Brill Lecture in Aerospace Engineering. Appreciate you being here. It's nice to see so many friends and colleagues. I need to start. My name is Bobby Braun, and I'm a member of the Aerospace Engineering section in the National Academy of Engineering, and also a fellow of the AIAA. And I'll be emceeing this event for both societies today. Very happy to be here with you. As we begin, I want to point out the emergency exits in the room. There are two to your right, one in the back. Please note the exit that's closest to you in case of an emergency. Hopefully there won't be such a thing. If we do have an emergency, we're to gather along Constitution Avenue, which is this side of the building. And finally, if you need the restrooms, they're located out these doors and to the left through the glass doors and straight ahead. As I said, my name is Bobby Braun, and in addition to being associated with these societies, I'm the head of the space exploration sector at the Johns Hopkins University Applied Physics Lab. On behalf of both AIAA and the National Academy of Engineering, let me say that again. On behalf of the American Institute of Aeronautics and Astronautics, in case you don't know, and the National Academy of Engineering, I'm very pleased to open the Yvonne Brill Lecture in Aerospace Engineering and to welcome you. This lectureship, the Yvonne C. Brill Lectureship in Aerospace Engineering, was established in 2013 in memory of Yvonne Brill, who was a pioneering rocket scientist and both AIAA honorary fellow and an NAE member. She was a trailblazer at a time when women were not encouraged to enter the fields of science and technology. Yvonne truly embraced the spirit of AIAA, and it's quite obvious through her contributions that she shaped the future of our profession. She did so through the invention of revolutionary propulsion systems, and in particular, the hydrazine resistor propulsion system that's used in attitude and control systems in a large number of geostationary satellites today, and has also been used on a handful of interplanetary spacecraft. As a young engineer in the field, I'll never forget going to the Joint Propulsion Conference and actually getting to meet Yvonne. I had just graduated from graduate school with a master's degree, and she held court in this conference. All the young engineers wanted to meet her, talk to her, learn about her career, and learn about the profession. In addition to her technical contributions, she certainly also shaped the future of aerospace for women. She was an active voice for women in science and engineering, helping to ignite the understanding that one's gender has no bearing on one's ability. And she was a pioneer in her time in a very male-dominated profession, where it was common to think that women may have been unable to tackle the hard problems that our community regularly solves. Yvonne proved that was not the case. This lectureship, named for her incredible contributions, emphasizes research and engineering, issues for space travel, exploration, aerospace education of students and the public, and other aerospace issues, such as ensuring a diverse and robust engineering community. We're all better for the contributions that Yvonne made to our profession and our society. Now I have the honor of introducing the 2024 recipient of the Yvonne C. Brill Lectureship, and that's our own Dr. Penina Axelrad. Penny is a distinguished professor in the Ann and H.G. Smead Department of Aerospace Engineering Sciences at the University of Colorado Boulder. She earned her bachelor's and master's degree in aeronautics and astronautics from MIT, the Massachusetts Institute of Technology, in 1985 and 1986, respectively. And in 1991, she earned her doctorate in aeronautics and astronautics from Stanford University. And I should say it's at Stanford where our paths didn't actually cross for the first time, But when I got to graduate school at Stanford in 1991, everyone was still talking about this PhD student that had just graduated, Penny Axelrad. And since 1992, she became a faculty member in aerospace engineering sciences at the University of Colorado Boulder, with a focus on astrodynamics and satellite navigation. She also served as department chair for that department from 2012 to 2017. Penny has supervised 26 doctoral graduate students and taught courses on topics that include GPS, dynamics and systems, spacecraft dynamics, and estimation theory. Penny and her students have made key contributions to GPS receiver autonomous integrity monitoring, to GPS-based attitude determination, the characteristics of multipath effects in GPS measurements, the utilization of reflected GPS signals for remote sensing of the Earth's surface and direct positioning. And her current research interests include new technologies and algorithms for position navigation and timing in space, airborne, and in land environments. And you're going to get a significant dose of that background and experience in today's lecture, which should be fascinating. Penny is also a member of the National Academy of Engineering and an AIAA fellow. She's also a fellow of the Institute of Navigation, and she's the past recipient of the AIAA's Lawrence Sperry Award, the Institute of Navigation Johannes Kepler Award, and the Women in Aerospace Educator Award. It's my distinct pleasure to welcome the recipient of the 2024 Yvonne C. Brill Lectureship in Aerospace Engineering, Penny Axelrad, to the podium to present her lecture, The Evolution and Impact of Global Navigation Satellite Systems. Penny?
Thank you very much for that introduction. And thanks to the AIAA and the National Academy of Engineering for my selection for this. Sorry, I have to put my glasses on. I want to start by saying that I'm ever grateful for the mentors who got me started on GNSS, GPS and GNSS. John Kelly at Hughes Space and Communications in 1985 introduced me to the idea of using GPS for space navigation. And then starting in 1986, my PhD advisor at Stanford, Brad Parkinson, who throughout my career has opened up tremendous opportunities for me to do all kinds of interesting work for almost the last 40 years, which is kind of shocking, actually, when you get there. At the time I started working on GPS, it was pretty much unknown. So the person sitting next to me on the airplane or the chairlift wouldn't necessarily know what GPS was, but they would say, oh, that's pretty interesting. About 15 years ago, the person in the seat next to me would definitely know what GPS was, but they probably would have thought, well, why would you still be doing research in that? It seems like a done deal, right? And then where are we today? So today, people know that GPS is everywhere and we depend on it, but they also understand that there's some risks associated with that. The fact that we are so dependent on GPS and we have to think about what happens if there's something that interferes with it. So what I want to talk about today is the evolution of GNSS, the more general version. So GPS, the Global Positioning System, was the first one, but now there are multiple global navigation satellite systems available. And what I want to talk about is the evolution of the technology and the applications to where we are today and what might be the direction that we head in the future and how those two things are interconnected. Okay. So global navigation satellite systems are a tool looking for a problem. This is a direct quote from a rejected NSF proposal that I submitted in the mid-1990s. So it was it wasn't science driven enough. It was GPS. You're just trying to look for things to do with GPS. And the fact is, actually, they were right. That was true, but it's not a bad thing. GPS is really quite amazing. It's constellations of signals being transmitted to us for free and they are stable and they're always available. And so they're basically out there inviting us to use them for different things. So we can not only use it for positioning, but we can actually use it for timing and all kinds of other creative uses because they're out there probing the environment for us all the time. And so I'm going to talk about how that flip, right? The idea of it's not just doing the things that it was set up requirements for, but it's actually enabling all kinds of new inventions, new discoveries. I think that that's the part that's really exciting about it. So the thing about GPS is initially that was so transformative is the fact that you could go out there and use it with no preparation. You didn't need anything besides your receiver. You didn't have to set up a base station. You could just walk out in the middle of nowhere and do positioning and do timing. Everything fundamentally is based on time transfer and timing, right? So inherently, you could bring time and stable frequency into any place, anywhere in the world, again, with no additional preparation. It's so addictive, right? You didn't have to do all kinds of stuff. You didn't have to look at a map before you started navigating, right? That's where we ended up. But so that was the important part about it as a standalone system. And then once you started incorporating other things like maps and monitoring stations and other types of data, you could suddenly do things like surveying and turn-by-turn navigation control in your car and autonomous guidance of tractors and aircraft landing systems and all the other things that have come with it. So what is it that's so fantastically great about GNSS? Okay. It is dual use, and it was always intended to be, right? So it started out as a military system, but the intention was from the very beginning that would also be available to the civil users because we would all be paying our taxes for it. So from a very practical perspective, I don't think there was ever any intent that it would not be available to civilian users or commercial users in some way. It's quite accurate. So even the standalone accuracy of it by itself, came in at the few meter level initially. Now it's still at the few meter level when you don't do anything special. But it turns out that you can quickly get to decimeter, centimeter level with all kinds of additions that have come in beyond that time. It's globally available. All weather, it's pouring outside, GPS works perfectly fine. It's raining, it's snowing, it's dark, you're in the middle of nowhere, in the middle of the ocean, or you're in a city. You can do it, infinite number of users can use it all the time. So the way it was designed in order to serve that purpose for every user everywhere, except indoors, kind of, is really transformative. I guess one of the other things I'll say about GPS is anytime somebody tells you that GPS can't do that, you should be a little skeptical because initially they said GPS doesn't work indoors. Well, nowadays with our cell phones, it kind of does work indoors. And people, well, I'll tell you about some other applications where people said, no way, it can't do that. But in fact, it does. So that's why it's so addictive. It's self-contained and passive for the user, which means that you can, from a military perspective, this was a very important requirement because you wanted a soldier who's behind enemy lines to be able to use GPS and figure out where they were without having to transmit a signal. And so that was very important from that perspective. But it turns out that's also incredibly important from the power perspective. So the reason you're able to use GPS in cell phones and CubeSats and other places, drones, where it's very power restricted, is because it doesn't have to transmit anything. So it's totally passive, and that's quite important. Receivers are cheap nowadays. Okay, they didn't start out that way. The first receiver I worked with was a Trimble receiver with separate board for each channel, and I don't know how many thousands of dollars it cost. But now the chipsets that go in your phone cost less than $20. The other part that's interesting is there's no fees to users or manufacturers, and this was not always the intent. Over the years, the US and other countries had tried to figure out how to charge people for GPS. And nobody could ever come up with a very good way to do it, which is terrible news. No, it's great because it means we all were able to do it. But they couldn't figure out really how to charge anybody to make it work. So now there are add-on services that you pay for, but the fundamental GPS signals really are out there for free, which is great. The US system put out documentation of the signal right away. And so that got people hooked on it. It meant that people could build GPS receivers in any country in the world, right? Because all the information was out there for the civil signals. There's restricted documents as well. What happened though was that when that happened, the follow-on system, so even GLONASS and Beidou and Galileo ended up putting out signal specifications as well. Why? Because they're great people, but also because people were able to figure out what was in those signals without anybody actually telling them. Because if you're out there transmitting signals all the time, people can capture it and then essentially reverse engineer it. And that's what happened initially with GLONASS and Beidou, is there were graduate students at various schools who tracked signals and spent days and nights figuring out what was likely there and were able to use it. And so then in the end, all of the operators of GNSS have put out open documents on some parts of their signals, which has made it incredibly powerful for all of us. And then as a teacher, the other thing I love about GPS is how multidisciplinary it is. You cannot think of a single topic, economic, political, maybe religious, but signals, astrodynamics, orbits. There's so many different things that come together to make GPS work or GNSS work that has just been a fascinating ride for me as a researcher. And it's a really good way to get students interested in all kinds of aspects of science and engineering. So here's classic GPS. Okay, we have our space segment, which is the satellites. Each satellite has multiple atomic clocks that create stable signals that are essential to the operation of GPS. We have the control segment down here. It's headquartered at Schriever Air Force Base in Colorado Springs, where the satellites are controlled by 18-year-olds sitting in front of computers, occasionally uploading data to them. And then there's the user segment, those of us flying around in our F-16s and driving around and holding our cell phones. And this is the fundamental pieces of GPS. Some key dates there: 1978 was the launch of the first GPS satellite. 1983, the Korean airliner that strayed into Soviet airspace and was shot down. After that, President Reagan offered GPS free to the world forever. So it was available to everybody before that, but that was sort of a commitment at that time that we would continue to do that. One of my colleagues called that spectrum dumping at the time, right? It meant that we were basically forcing everyone to depend on GPS because it was free. So when GPS was first set up, the initial intent or expectation was that the military signal would be more accurate than the civil signal, right? But it turned out that smart people figured out how to get good results out of the civil signal, and there was virtually no difference. And so then they implemented this thing called selective availability, which is a euphemism for we're going to mess up your signal, and it would wander around by 30 meters when you're standing still. So it turns out in 2000, President Clinton decided to end selective availability. It turned out it was done in May of 2000, which I remember very distinctly because I was teaching an electronics course where the last lab of the course, we were using GPS. We'd give them these little Garmin receivers, and the students would run around and do positioning. And I would say, you'll be standing still and you'll see your solution wandering around like this. And they came in on Monday, this is over a weekend, they came in on Monday and said, it's not wandering around, it's just sitting there. I said, well, something must be wrong, Sure enough, that was the weekend they turned off selective availability. So this is a picture on the left of the GPS constellation, but on the right is a list of the current active GNSS satellites. There are about 140 of them currently active. 31 GPS satellites, 24 GLONASS, 24 Galileo, 44 Beidou. Then there's some additional ones. All of the fundamental, there are 4 basic constellations. All of them are in medium Earth orbits. So medium Earth orbits have an orbital period around 12 hours, which means they're not GEO. They don't stay frozen there for the whole time. They go around twice a day. And they're not LEO, so they're not going around every hour and a half. They're somewhere in between. That has tremendous advantage. With MEO satellites, you were able to get completely global coverage with just about 24 satellites, right? So you could use GPS to position anywhere on Earth with only GPS. You didn't need anything else. So you would say, well, why did all these other countries or the European Union put up their own constellations? Obviously, for sovereignty, they want control over it. They want to be able to use it for their own defense purposes, which makes perfect sense. The good news is there was coordination of the spectrum. And so all of these different GNSSs can operate in that same frequency band without interfering with each other substantially. So all of the codes, all of the signals have been designed from a cooperative perspective so that all of these entities have the ability to use it for their own purposes, but are also essentially not preventing everybody else from using them too. Okay. In addition, there are a number of augmentations. So for example, QZSS is a Japanese augmentation that provides additional regional coverage in Japan in that region. NAVIC is an Indian augmentation that provides additional regional coverage in that region. And then there are a bunch of others called SBAS, because you can never have enough acronyms, right? Space-based augmentation systems. That provide correction services to the fundamental constellation signals. So they tell you how to improve the accuracy of those signals. So that's the picture. And in case you're wondering what satellites we can see in the sky, this is 11 o'clock this morning, Washington, D.C. These are all the GNSS satellites that are above us. And this is a sky plot. So the center of the bullseye would be directly overhead. And then on the blue rim would be directly north at 0 elevation, so right on the horizon. So there are over 30 satellites that are visible to us at this time, not inside this room, but if we went outside with a pretty clear view of the sky, we would see 30 satellites. You only need 4 to position. So that's a huge amount of redundancy. So when you're able to track multiple constellations, even the GPS by itself, you have 8. You have a huge redundancy, which gives you actually, if you use it properly, a lot of integrity and a lot of resilience, right? Because you can actually see all these different constellations at the same time. And the hole there at the top, there'll be a pop quiz at the end for anybody about why there's that little hole there. Here's what the signals look like. So all of the GNSS constellations are continuously illuminating the Earth and beyond a little bit with signals that you can use for PNT. Okay, so these signals are coming out 24/7. They're in this L band, which is a magical frequency band because it's not affected very much by weather at all. And it has a lovely dependence on the ionosphere that is inversely proportional to the square of the frequency, which means if you send out signals on multiple frequencies, you can basically correct the ionospheric effect. So those are really good properties. And that's why other people want this frequency band, right? Because it works really well for communication or other things. But navigation is a special user because not only do we want to get the signal, but we want to have a very predictable path of the signal to get to us, a very clear path for the signal to get to us. And so that's been really instrumental, again, in why it's been so successful, because it has those features. Each of the constellations uses CDMA, code division multiple access signals. The Russian system originally was focused more on frequency division multiple access, but they have since imposed codes as well. I mean, they had codes too, but they're also using CDMA basically now. This allows all of them to transmit at the same time without a huge amount of interference between them. So that's been really critical. With the code modulation, receivers are able to measure the range to the satellite, and they also use the carrier signals to measure carrier phase and Doppler. And the carrier phase is what allows all the high precision applications to be done. So that's been really critical as well. In addition to receivers that are tracking all these signals for positioning, some of them actually also capture signal distortions. So they can tell when a signal has come to you not on a direct path, but in an indirect path. And they can look for distortion that's a result of ionospheric activity or other effects like that. And so that has turned GPS into a great tool for remote sensing as well. Okay, so basic positioning. If you have perfect clocks, you get a transmission, it puts you on a sphere on the transmitter. You have 2 of those, it puts you on a circle. You have 3 of those, you get your location. If you don't have a good clock on your receiver, you actually need 4 satellites. So that's the quick intro to GPS. And so you stand around with your receiver, you track at least 4 satellites, and you can get a full 3D position, 3-dimensional position, lat, long, height, or XYZ, and, off you go. And you don't have to sit there for very long. Receiver can make that measurement in well under a second. It takes a minimum of a millisecond's worth of data. Most receivers will do it 10 milliseconds, 100 milliseconds, but you can get answers quite quickly. Okay. So what happened when people started using GPS? Okay. So you start using GPS and you start thinking, well, my accuracy is good to 10 meters. Initially it was. Why was it 10 meters? Because initially the orbits of the GPS satellites and clocks weren't known that well. And that was really the limiting factor. And if you had a single frequency receiver, you were also limited by ionosphere. So what do? Well, we find ways to get better orbits and clocks. It turned out you needed more observation stations on the Earth to get better estimates of the orbits and clocks. Okay. What do you deal with, $20,000 receivers? Well, you figure out how to build smaller, cheaper receivers. That makes a big difference. Then more people have them. So you have more GPS observations in more places and off you go. Well, then you say, well, hey, I'm noticing the effect of the ionosphere on my signals. Well, what if I turn my receiver into a science instrument and suddenly I can study the ionosphere with this thing that was supposed to tell me where I was, right? And then, okay, I'm not a soldier in the middle of nowhere or a ship out in the middle of nowhere. I'm in a city, I'm in different places. What if I loosen some of those restrictions on everything having to come from the satellites? Suddenly I can open up all kinds of new applications. And so there's this virtuous cycle of more information, you notice more things, you get more information, and you can create this entire infrastructure of great applications that came from GPS. So here is a few examples. So when I was putting together the idea for this talk, I realized, well, I teach an entire semester's worth of material that would be interesting to all of you, I'm sure, but I just have a few examples. So will not cover everybody's favorite example, and I will definitely not mention any names because I decided it was impossible for me to do this without skipping somebody important. So here's a few starting points. So again, in the early days, one of the first things people realized was that the orbits and clocks were a limiting factor, and then also ionospheric effects. So the idea of differential GPS started pretty early, where you could set up a local station at a fixed known location, and it would send range corrections, pseudo range corrections to users nearby. Okay. And then suddenly those users nearby would have accuracy at the level that the fixed station was, right? So that got rid of, if you had a fixed station nearby that was sending out these corrections, you essentially weren't suffering from the limitations of the orbits. The downside is you did need a radio now to pick up the signals from these local stations, and it means somebody had to set up these local stations, okay? So that's great. You got your accuracy down from tens of meters. And again, in the days of selective availability, it got you down from 30-meter positions back down to a few meters, right? So the government was messing up our signals and then also providing differential stations to correct our signals. But they were local. And then you said, well, if I could have, decimeters, why can't I have centimeters? So if you have a base station and it not only sends you code corrections, but actually sends you carrier data too, okay? You can actually then, and it's known location, you can actually solve for the relative position at the few centimeter level in these regions. And so you can do real-time kinematic. That has progressed so far now. So if you use drones nowadays, you can easily set up a base station in 10, 20 minutes, let it run, and it will broadcast the corrections to the drones flying around in your little area that are good to 10 centimeters. So with no hassle, it's really turnkey, and that's quite amazing. The downside is you still need your little local station. So that's a problem, right? If you want to go out and not have to worry about that, maybe that's a little bit too much of a hassle. All right, let's look at receivers now. So this was the early GPS portable sort of receivers were these ones on your back. There's an even earlier picture of a giant thing that you had to sit down at a console for, but I skipped that one. 1978. In the 2000s, we started to have these handheld garments. How many people here had one of those? Okay, these were the ones my students were running around with at the time the selective availability turned off. The receivers were actually going in two different directions at that time. There was the handheld things, and then there was the scientific ones. And so this is equipment from Trimble that was used for a lot of geodetic applications, and they were deployed throughout the world, even Mount Everest and all kinds of places, for really making very precise geodetic measurements. Fast forward another 15, 20 years, and you have lovely watches that were huge. And you have modules that could be used not only for pretty much any application. So ground-based, land-based, you can buy space versions of these things. Small modules that you could put on a low-power device, and they would collect raw data, and they would also do positioning for you in all kinds of different modes. And then 2022, I mean, the first chipsets came out before this, but Dennis Akos pointed me to this one. The Broadcom chip in 2022 came out. This is a chip that goes inside a phone. There's a breakout thing that shows it in a pixel that supports every one of the constellations at multiple frequencies at L1 and L5. This is incredible, right? I mean, that's really amazing. And yeah. Okay. Another really key contribution to the proliferation and real utility of GPS is the International GNSS service. So the IGS was founded about 30 years ago, and this is a voluntary federation of agencies all over the world that put out receivers, geodetic quality receivers, living up to specific capabilities, and they made their data public. So their data is posted on the web, and you can go and see data from every one of these stations, and they're all over the place. And there's some in really high latitudes and near the equator, and this data is out there for free. And there are a bunch of different sites where you can get it from. And to me, this is really remarkable. Like every one of these countries that's participating covers the expense of their own centers, right? Their own recorders. And then there are a number of different analysis centers. There are analysis centers all over the world, and they each do their own orbit estimates. So based on the data from all these different sites, they choose certain ones, and they use their own code to determine orbits and clocks. And then there's a coordination center that rotates around the different agencies, and they put out products. So all the products are there. You can pull up the orbits computed by the German organization or JPL or the Russians or the Chinese, and they're all out there. And then they also form a combined product. But the thing is, scientific users and engineering users have the ability to use any one of these things that they want to. You're not constrained to only the final version that somebody decided. They put them all out there. And so if let's say you're teaching hypothetically a class and some students don't believe you when you say it works in all weather, right? You can say, well, go check it out for yourself. And you can find a day of a horrible storm anywhere in the world. You know, you look for one of these dots on the map, and you can download the data from that spot and look at the data on this terrible storm day and on the day before and the day after and a week later, and you can see what it looked like. So this was huge from a research perspective, because suddenly you didn't have to go out and do a campaign necessarily to make the measurements you wanted. You could actually go harvest the data. We didn't call it data mining in those days, but you could go look for stuff and find data to help you answer scientific questions that you were curious about. So quite remarkable. And also was incredibly valuable for people developing new techniques for using the data, because they had lots of places to go without having to run their own experiments. So this actually had a big impact on positioning accuracy too, because remember we talked about differential GPS and RTK. With global networks of receivers all over the place on the Earth, you could also do something called precise point positioning. So this means that you can now get differential corrections, you can get improved orbits and all these other fancy products without even having a local station. Because all these agencies that were, part of IGS, and also commercial companies now, are putting out their own networks and providing, and here's where they do figure out how to charge you. They are putting out products that are higher precision, centimeter level, that you can actually get in real time due to these global networks. So this has been a remarkable transformation from my perspective. Okay. And they have all kinds of corrections in here: relativity, troposphere, ionosphere, phase center variations in the antennas. Like, you can quiz me on whether they include that, but it's in there, you know? Okay, so now we're going to turn to a few different special applications of GNSS. So the first one is aviation, and it was clear from the very beginning that GPS was going to be very important for aircraft navigation. The hard part with it is the current system, or the way the system is set up in the United States, is it doesn't have the integrity. It doesn't have a way of checking whether the answer it's giving you is as accurate as it's supposed to be, right? So inherent in GPS, eventually it can tell if a satellite has failed or something's wrong, but it takes way too long. It's not, if you have an aircraft on approach, it wouldn't be able to do it by itself. So stepping away from everything has to come from the satellite itself, the wide area augmentation system was developed by the FAA and the Department of Transportation as a way of bringing that integrity into aircraft navigation. And so, again, if you wanted to have local stations everywhere monitoring, it would take lots and lots of them to cover the United States. What they did with the wide area augmentation system is they developed a network of 38 stations that monitor it all over the US. And their data is brought together to create sort of vector corrections of accuracy. But more importantly, it provided integrity. So it was a way of quickly checking whether something was wrong with the signal. And within 7 seconds, this system would be able to tell receivers that something's wrong with a particular signal. Now, how do you do that? Well, the key thing was they had this network of stations, but they didn't distribute it by a separate radio signal. What they did is they uploaded, so there's a central area where the results are calculated, and then they get uploaded to geosynchronous satellites that stay fixed in the sky. And there's 3 of them that are over the US. So the signals are sent up, or the information sent up to those satellites, and the geo satellites transmit at the same GPS frequency. So they look just like GPS satellites, but they're in geo. And that allows your receiver, your simple handheld receiver, or one of the other ones, to get that integrity directly. So there's no extra radio link. It's coming through the same type of system. In the United States, it's not part of the current GPS, right? It's a separate system run by the FAA, the Department of Transportation. In the other constellations, so for example, in Beidou, it's built into it from the beginning. So the Chinese system is a newer system, so they immediately implemented this same kind of feature in their existing GNSS. And here in the United States, it's just a joint effort between the 2 different programs. So that made it possible for aircraft to land. It allowed for much more flexible approach and high integrity of the air system in the United States and in the world. It meant you could land at different places. So there are different augmentation systems in different regions of the world that provide the same kind of integrity feature when you're not over the United States. Here's another one. How many of you thought we'd really be navigating with cell phones? I certainly did not see that coming, right? So what makes GPS useful in cell phones? Clearly the availability of the maps, but what's most important in cell phones is low power and low cost, right? That's really key. So in order to make it work, you needed the kind of chips like the Broadcom chip, but your phone, the early GPS in phones was really bad. It drained the power from your phone in no time. So what changed was this idea of assisted GPS. So the phone networks have a network of reference stations, and they feed information to your phone that lets your phone acquire signals super fast. So your phone is not hunting around for everything in the world. It knows pretty much where it is, and it knows how to pick up those signals very, very quickly. And they implemented this, so there's this assistance data that comes in and allows your phone to get an answer instantaneously, and also it doesn't need to track continuously. So this is a huge impact. This is why it works so well. And it also is why your phone can actually pick up signals indoors and like in subway stations sometimes, which freaks me out. There's some other interesting applications. we were talking about, can you use GPS everywhere? Urban canyons are a really tough place to use GPS, right? Because the signals are not rarely coming to you direct. There's just that little piece of sky. So people have worked on interesting new ideas for how to deal with this. And that is, if you have a digital elevation map of your city, then you can use the signals you get directly, and you can maybe also use the signals that you don't get, right? I'm not getting this satellite, so maybe that means I'm over here in this shadowed region. Or maybe you can tell when you're getting a reflected signal or one that's going through a building. So there's this concept of shadow matching that's been kind of interesting application. And then there's this idea of direct positioning. So this is a picture of, normally a receiver tracks each satellite separately and then forms measurements and then combines them to get an answer. The idea of direct positioning is, instead of tracking each satellite separately, you actually combine the correlations and you look for an answer that's consistent with all of them at once. And that allows you to use information from signals that are too weak to track separately. You can, still get some benefit from them. All right, my favorite application, of course, is space applications of GNSS, which was, again, totally transformative. The first, of course, is onboard position and time. So pretty much every LEO satellite uses GPS for positioning, and that's part of what makes it so feasible to have constellations like Starlink and OneWeb and all the other ones up there. Is you don't have to track them from the ground in order to determine their orbits and time. So that's a really important and potentially vulnerable area. But LEO satellites are zipping all over the place. It's hard to interfere with all of them at once. So that's good news. But so GPS is used for onboard positioning and timing, also Doppler and carrier phase. And one of the most accurate things you can do with GPS is do orbit estimation of low Earth orbit satellites. You can actually figure them out at the centimeter, sub-centimeter level if they are scientific satellites, and you use really fancy software with all those ground station data too. Other things that have been done are formation flying. So flying satellites in formations for things like mapping of the Earth. This is a formation flying between Tandem X and TerraSAR X. This is Sentinel-6, which is an altimetry satellite. So it uses GPS, high precision GPS for the orbit. It uses an altimeter, of course, to measure the ocean surface, to measure the height above the ocean. And then if you want to know the height of the ocean, you would subtract those two. Formation flying for the GRACE satellites, they use a laser here, but they also use GPS for the orbits. And then there's other satellites. This one is Cassiope. It's a Canadian satellite, and they had multiple receivers. I think they had 5 of them on there, so they could actually use it for attitude estimation as well. So looking at relative positions of different antennas, you can actually figure out which way it's oriented. Not as accurate as a star camera, but still pretty cool. And then finally, I don't have a picture of this one, but GPS is now being used above the constellation regularly. So in geosynchronous orbit, the GOES satellites are using GPS for doing their orbit estimation because it's a lot easier than ground station, and it's actually more accurate. Here's the next thing. There's a plan to use GPS at the moon. Okay, there's a NASA ESA mission called LUGRE that is going to fly a spacecraft all the way to the moon and use GPS all along the way. So it'll be used during the phasing orbits. They're planning to use it on the lunar surface as well to measure it and see how it will perform. The signals are really weak when you get to the moon, right? Because you're seeing them past the limb of the Earth. But it turns out with a high gain antenna and a good stable clock, you should be able to track them. So this will be an interesting experiment. We'll see how it works. And yeah. Okay. There are a bunch of different science applications as well, and I'm not going to talk about all of these, but as soon as you put high quality receivers in different environments, you can sense all kinds of things like ice sheet motion, earthquakes, time variable gravity, effect from orbits. And it turns out that with the Galileo satellites, 2 of them got accidentally inserted into elliptical orbits, and they were able to use those to measure relativity at a level, the equivalence principle at a level that was about an order of magnitude better than it was known before that. Again, not an intentional failure, but it turned out to be interesting from that perspective. You can map the ionosphere and the atmosphere and all kinds of other things. So this last one, I don't have a slide on, but so it turns out if you have a GPS antenna and you look down towards the Earth, you can pick up signals reflected from Earth's surfaces. You can use that to measure ocean surface winds because of how it creates roughness on the ocean surface. And you can use it to sense water inundation in land surfaces because suddenly you get a shiny, smooth area over the land. All kinds of interesting applications there as well. One of the important ones, I think, has been the contributions of GPS to measuring sea level. So here's a plot of mean sea level since 1992, roughly, when TOPEX was the first satellite that had GPS on board for scientific purposes. And here's a measure of mean sea level rise from a sequence of satellites that all use GPS for their orbit estimation. So Sentinel-6 is the most recent one in that time series. Here's another, I think this is maybe one of the most surprising examples. I told you GPS isn't very sensitive to weather, okay? However, if you have a low Earth orbit satellite, and instead of looking straight up at the satellites, you look straight up, but you also look down towards the limb as the LEO satellite is setting, and here's a GPS satellite, that signal gets bent by the atmosphere. And it's slowly, over about 100 seconds, not so slowly, over about 100 seconds, that signal goes down through the atmosphere. And as it's going down, you get a bending and a delay of the signal. And by looking at the carrier phase of those signals, you can actually infer the atmospheric density, and from there, the temperature and other aspects of the atmosphere. And data, and this is called radio occultation, GNSS radio occultation. It turns out this data is feeding into numerical weather prediction models. So when they predict rain, part of it is actually based on data from constellations of low Earth orbit satellites that are tracking GPS as it sets through the atmosphere. So it's quite remarkable. The other way to do that is with balloons, right? You can put balloons up and measure it, but that's a lot less convenient than just putting up a handful of satellites and measuring these effects. Okay. Here's a shout out to the ION satellite division. So in 1987, we had 1986, I think, was actually the first one. The satellite division of the Institute of Navigation had a conference dedicated to GPS. We just had our most recent one a few weeks ago. This is a gathering of all the GNSS nerds in the world who get together and talk about what they're doing. And this has been an amazing place where people came, the leaders of all the organizations would come and talk about what's going on with their systems. Scientists would come, engineers would come, and there was this great exchange of information about the kinds of things you could do with GPS. And it's been really remarkable to see the range of topics that have been happening there. And as you can imagine, right now, the hot topic these days is LEO, low Earth orbit augmentations, and also interference and jamming and spoofing and that sort of stuff. So it's been really interesting. Okay, so what could possibly go wrong? Current challenges right now are anytime something is too good to be true, it's too good to be, well, kind of too good to be true. So there is a risk. This is the GPS Jam website, and it shows you where there's interference, people deliberately probably messing with GPS, transmitting signals that interfere with GPS. So you have to worry nowadays about jamming and spoofing of GPS signals. And as we become more and more dependent on it, say for self-driving cars, okay, we worry about that, right? So what can we do? I think the answer is not we say GPS is useless and that's silly, right? But what we should do is add other resources. So as I showed you, there's so many constellations out there. If you have multi-band redundancy. That is, you have multiple constellations transmitting, you're using all the different frequency bands. The likelihood that someone is jamming and interfering with all of those at the same time is really tough, okay? That's much harder to do. And if somebody really is putting out that big a jammer, somebody could go take care of it because you can tell where it is, right? The other thing is, if you are in a place where there's a lot of other things, if you have in an urban environment or in a place where there's other infrastructure, you shouldn't turn off the ability to use your other things. You have vision-based systems, you can have LiDAR. If you are cooperatively working with other users nearby, you can tell if something strange is going on and you can bring in information from elsewhere. So if you no longer have to operate just on your own in the middle of nowhere, there's lots of good ways to find redundancy and realize that something's wrong. So for example, if you're in a region where there's a spoofer that's telling everyone they're at the Beirut airport, you're not all at the Beirut airport, right? So there's ways around it, and there's ways that you can bring in other kinds of technology, other resources to bring an answer. An important one, of course, is inertial aiding and stable clocks. And so we'll talk a little bit more about those. So for example, here's a couple examples. So multi-GNSS, right? So with the advent of all these other constellations, it's very important that receivers are well designed to use them. So most receivers now assume that you get L1CA. That's the basic GPS signal. If L1CA is being messed with, they won't get anywhere. So that's dumb, right? Because if you should be able to pick up a different signal and work with it and be able to tell in a more intelligent way which of them are reliable and which of them are not reliable. And as soon as you start doing this, you have to be careful that you don't get tricked in some other way. But of course, we have a lot of smart people out there who can figure this out. There's another interesting thing happening right now. The NTS-3, the Navigation Test Satellite 3, is an AFRL, Air Force Research Lab mission. It's supposed to launch in late 2024, although I'm guessing maybe it's been delayed a little bit past that at this point. But they're actually putting up this fancy multi-antenna transmitter that will be able to generate all kinds of different beams on the ground, and they have a reprogrammable signal generator on board. So they can actually test out different types of more modern signals. It's going to be a geostation or a geosynchronous satellite above the United States, and they'll be doing all kinds of testing with it. They will not put out a public document saying what all the signals are, but they will be able to test out more modern signals that could make their way into our receivers. In fact, there's a signal called Chimera, which is an authenticated civil signal that they're most likely going to be testing on that system. So I think that's really exciting news. Okay, low Earth orbit constellations. So in the early days of GPS, there was some discussion about, what constellations should they be in MEO, should they be GEO, should they be LEO? LEO was ruled out at the beginning as a really bad option. Why? Because it takes hundreds of satellites to provide enough coverage on the Earth. Who would ever put hundreds of satellites into LEO, right? Why not do MEO where you only need 20 of them, right? But nowadays, the game has been changed, right? We can some people can put hundreds of satellites, thousands of satellites up there. And so suddenly LEO is not as ridiculous as it once seemed to be. The downside is, of course, you do have a lot of satellites. So again, the ability to navigate, to do the orbit estimation of those satellites with GPS is pretty powerful. And if you had to track all of those continuously from the ground, that would be a pretty complex task, right? Because I don't know if you've thought about this, but LEO satellites go by in about 10, 15 minutes. So if you needed stations everywhere to track them, their orbits are a little bit less predictable than MEO. It's a complicated thing if you don't have GPS on board. But LEO is being considered right now in two different ways. On the left, I'm sort of trying to represent the idea of bespoke, like specifically constellations that are supporting PNT, right? Where you have low Earth orbit satellites that are kind of like the GPS satellites in that their main purpose is to provide stable signals for navigation and timing. The other thing on the right is this idea of, I want to say parasitic, but I don't mean it in a demeaning way, but the idea is using signals of opportunity where you're using Elon Musk's signals without him agreeing to it. right? Like any transmitter can be used for navigation if you can measure the Doppler, but you need a way to know what the orbit is. Well, they're not providing information about their orbits, but if you have enough ground stations tracking them, we know how it works. You can figure out what their orbits are. So it's more complicated. It's currently less accurate, but it has the ability to provide really almost an independent source of PNT on the Earth, but it requires this new infrastructure of people determining what those orbits are. And those satellites don't necessarily have accurate frequencies. They don't necessarily have great clocks on board. So there's a lot of logistics that goes into it, but it's been demonstrated. People are giving talks on these things. The next thing is networks of optical clocks in space. So right now, ground-based atomic clocks can have demonstrated stabilities at the order of 10 to the minus 18th. None of them are available in space yet, but if you could put clocks of this kind of stability into orbit, it would provide even greater accuracy and resilience for global navigation satellite systems. So in particular, there are atomic clocks and cavity stabilized lasers that the idea is if you can put these in orbit, it will continue to improve things. Once you have that, you also then need a way to transfer time at that same level of accuracy. So laser links can get you down to picoseconds. GPS RF stuff tends to be nanosecond. You want to get down to picoseconds, you can use laser links. And then to convert from the optical frequencies, you need something called frequency combs to bring that stability to RF. But these things all exist. Some of them have already been demonstrated in orbit. So there's a big move to try to figure out how this can all be used in the future. There's an interesting proposal from DLR for something called Kepler, which will be a third generation GNSS system, and they have a demonstrator of it called Compasso. But what they're proposing there is in low Earth orbit, they're going to put optical clocks, okay, very high stability optical clocks with an RF receiver, with a GPS type receiver in LEO, and up in MEO, they would have cavity stabilized frequency references and the RF transmitters. And so they're putting their monitoring station, they would put their monitoring system into low Earth orbit, still have the transmitters of the RF be in MEO, and this would have a tremendous improvement in the stability of the signals we get on Earth. They'll use the optical links between satellites and two-way time transfer to get that down to the Earth at reference stations. But again, most of the signals that we use would still be coming from MEO. So that's a pretty exciting potential opportunity. The other thing that has come up a lot is the idea of clocks, highly stable clocks, and quantum inertial sensors on the user side. So not on the global navigation satellite side, but actually on the user side. So the idea is that conventional inertial sensors can be very accurate, but only for short time intervals, right? Over time, they drift, you have to recalibrate them, or else they're super expensive and big, okay? There's this potential that with atom interferometry, you can get sensors that are accurate, but more importantly, that they have incredible long-term stability. So they may not be super more accurate than conventional sensors, but that they have almost no drift and require almost no calibration. And that's a really big impact thing. So there's a group at University of Colorado that's developing an optical lattice atom interferometer with the intention of doing accelerometers, gyros, and gravity gradiometers based on this technology. You can see here, this is actually an experimental result. And if you can combine these functions together, so the accelerometers, gyros, and gradiometer, you could potentially also use it for deep space navigation. So there's always this big issue of not knowing gravity field, but with the gradiometer, you'd actually have a direct measurement of that. So that's a really exciting thing. It's not quite ready to put on a small sat. This is what it looks like right now. But it's not a huge table. It's actually a small table, and this would be a full three-dimensional system for an accelerometer at the moment. So looking at the future, multi-GNSS, opportunistic multiband signals, I think are going to continue to enhance accuracy and resilience. If we do intelligent integration of GNSS with other sensing modalities, and I don't necessarily mean artificial intelligence, I mean intelligent meaning use things in a smart way, we'll see continued benefit from GNSS. I think the advanced clocks and quantum inertial really has a potential, again, not because it's super accurate, but because of the potential for the long-term stability that it brings. And then one thing I would hope to advocate for is this idea, like IGS did, if there's a way to continue to have widespread sharing of information, I think it will lead to really exciting future opportunities. So I want to end with a invitation to participate in International GNSS Day, which is October 23rd, in recognition of 10.23, which is the GPS, 10.23 megahertz is the GPS fundamental frequency. So the Institute of Navigation is promoting this, and I think it's really cool. So please celebrate International GNSS Day. I'll be glad to answer questions. Yeah, go ahead. Yeah.
They referenced it, didn't go into detail about that.
Oh, you have to use a mic. It's for the YouTube thing. Right? Okay, yeah. There's another one on that side too, if the line gets too long.
All right.
Yeah.
So L-band is also used for soil moisture.
Yeah.
And there used to be an interference of GPS signals over land in certain countries because of the interference of the frequencies. Has that been solved, or you changed, or how's the surface soil moisture? There's been an L-band used for that.
I don't know of a widespread use of, you mean like a L-band radar for that
Yeah,
purpose?
L-band satellites for surface moisture.
I haven't really heard of that. I know there's passive sensing of L-band, L-band
that's what I'm
radar.
talking about. It's passive.
So that doesn't cause interference with GPS. I mean, I guess maybe the presence of GPS signals could interfere with the radiometers.
Yeah.
But it doesn't go the other way. You're saying because there's too much L-band transmission right now. Sorry. Yeah.
So you showed mostly circular orbits, but my understanding is that there's some consideration for highly elliptical orbits. Can you talk about that?
Yeah, the elliptical orbits. So the inclined geosynchronous satellites are, some of those are a little bit elliptical because what they want to do is dwell over that region that they're servicing, for a longer period of time. So some of those regional systems actually do use somewhat elliptical orbits. So none of them are super elliptical.
I thought the Chinese were coming up with a super elliptical orbit for dwell time.
Yeah, so they have theirs are so in the regional. So again, for the satellites that don't really cover the whole Earth, but just cover particular regions, they put them in inclined orbits and also somewhat elliptical so that they dwell over the region. They spend more time. They're sort of at apogee over the region they're trying to service, and then they zip by the other parts of the world. And, they do that like figure-8 pattern kind of thing, and they definitely will hang out there a little bit longer. None of the systems that I know of are deliberately doing very elliptical orbits. One of the downsides of having a very elliptical orbit is that unless you modulate the power you're transmitting, it would create a much larger dynamic range of signals you have to pick up. Right now, they're all designed to have pretty even levels of signal power on the Earth's surface. But the Chinese also are including geo satellites, and they also put LEO, low Earth orbit satellites, in their constellation to monitor from below, actually. So they're not transmitting L-band signals from there, but they're monitoring the upper ones. Yeah.
Oh, thank you. Your wealth of knowledge was incredible, and I really appreciated you sharing it. So, of course, I'm going to reward you with the questions get a little bit outside of the science and the technical aspect. I was so encouraged by what you said about, there was so much collaboration or coordination in the GPS world between countries of kind of making sure they weren't going to be in each other's orbit and cover the Earth. And As you know, right now, though, we're having this whole issue of what's going on in Leo, and it's just kind of a, a food fight.
Right.
We're doing our part here in the U.S., Rich Del Bello and Department of Commerce, and they seem to be doing a great job. But that whole issue of how do we coordinate internationally seems to just be kind of an open-ended question. I'm just kind of wondering if there's something that really be learned. Were there certain things that your community did that really helped kind of move in that direction? Because it also has international security issues. What you're using is very similar to the concerns that they would have in this other realm. So it's something we really have to deal with.
That's a great question. It's interesting because it has both technical and obviously a lot of political ramifications. I think one of the things that has always puzzled me related to the getting the ability to launch satellites is it's mainly been focused on what you're transmitting and less on making sure that you take good care of the orbits and avoid collisions and all that sort of stuff. So I don't know whether that has changed from a regulatory perspective. That's outside my expertise. But it used to be more, as long as you got permission to transmit your signal, there was less concern about those other aspects. And I don't know how that's currently being handled, honestly. I'm sorry.
Yeah. It's starting to be addressed now, but we're doing it in our country, but that doesn't mean it's coordinated with anybody else's country or that they're doing it. So it's a big issue.
There's actually an interesting side note is we used to not worry about the decay of the MEO satellites, right? MEO is medium Earth orbit, is not very crowded. But Aerospace Corporation actually did some interesting studies on how the medium Earth orbits would evolve over time. GPS satellites are put into what they call a graveyard orbit, like a higher orbit. But they did some studies, it's been a while now, but they showed that eventually in like 50 years, they are going to start to decay. The orbits get more and more elliptical and they start passing through the other constellations. So, even MEO is not totally safe anymore.
Thanks.
Thank you. Yeah.
Yeah. Hi. Thanks, Penny. That was a great review of the past and the present and a little bit of the future. Now, I'd like to ask you something totally off base.
Okay.
What do you imagine we're going to be using for navigation when we're traveling in interstellar space?
Oh, quantum sensors, for sure.
Okay. And how are they going to work?
I mean, when you go into interstellar space, you mean?
Way out, way out.
Way out. Yeah, it's going to be like SLAM, simultaneous location and mapping, right? You're going to be mapping gravity fields at the same time that you're figuring out where you are. You're going to have intersatellite links between a group of things that are traveling together, kind of like a bootstrapping system, right? Where you are putting out guideposts and finding your way.
But there's not going to be much gravity for most
True.
of the trip.
You'll have star trackers too, right? That you're going to need that for sure. I'm sorry.
Maybe not quite as far reaching as that question, but
Good.
this is probably another lecture altogether. But
Yeah.
can you maybe touch on what we're doing to bring some of these GNSS capabilities around the moon and cislunar space?
Yeah, that's a really good question. Right now, so there's a few different things going on. One is people are looking at using existing GPS, right, to get out there. So there you're looking at the spillover from the sides of the patterns that are already going there. People are looking at putting constellations, the Gateway and satellites in non-rectilinear halo orbits and things like that to support lunar operations. I'm a big advocate, though, for using pseudolights on the surface because there are not that many users out there, right? So GPS or GNSS makes a lot of sense when you've got billions of users or even millions of users. But if you're talking about operations on the moon or even Mars or places like that, the number of users isn't that huge. So my opinion, and it's just my personal opinion, is you're probably better off starting with surface-based transmitters augmented with GPS and maybe a couple of orbiters rather than trying to do a single system like that. And you can get a lot of leverage by using two-way systems. So instead of just passive, if you have a small number of users, having a two-way link could actually be a more efficient way to get started. But I'm not on any official panel or anything like that about it. Hey.
Yeah, hi, Professor. Thanks so much for the lecture. I was curious if you could talk a little bit about your work serving in an advisory capacity for the government on this subject, and sort of what is the role of that advisory apparatus, and maybe if you could kind of distill from where you're sitting right now on what are sort of the top of mind challenges in this space for your agency colleagues. Thanks.
So I'm not on the panel anymore. I have been a member of the P&T Advisory Board for about 10 years, but I recently stepped off. It's actually a really interesting organization, right, where they bring in experts on GNSS and also international people to provide advice to answer questions that are posed by the organizations, so the Department of Defense, Department of Transportation, things like that. I think we've made recommendations in the past about resilience and backups and what kinds of things need to be worried about. It's the process by which those get absorbed. I don't really have any visibility, so I don't really know. I'm not a policy person.
Think about
I can read. Yeah. So the question was, what is my most interesting personal contribution to this? You got to ask somebody. No, I think, you know, as a teacher, right, as a professor, I think that's probably been the most interesting thing, because I had the opportunity. I've been teaching GPS now for 30 years. And just, okay, everybody who comes in to the university wants to do interplanetary trajectories, right? All the astrodynamic students want to do interplanetary trajectories. So probably the most interesting thing I've done is convert a bunch of them into satellite navigation experts. So I try to teach a GPS class and expose them to all the fascinating things that come together there. And then they go off and do really cool things. So.
There you go. So thank you, Penny. That was a great lecture. I think we all enjoyed it. Really interesting and educational also. So you met the bar for your professor and teacher perspective. So thank you very much. And thank you to everyone who is online, who has joined us personally or physically here at the NAS building. Before we conclude, I have the honor of presenting you with this amazing plaque to commemorate. Can we walk over here maybe? To commemorate, you know, your the 2024 Yvonne Brill lecture. So I'd like to present this. Also, no, stay. I'm adding to the program. So also, I've been informed that there are several members of Yvonne Brill's family that are here with us today. Matthew, Logan, Ellen, maybe others. If you're a member of the family, would you please come up for a photo? Where'd our guy go? Can we get one more photo, please? Is that? Oh, okay. Go ahead. You all get in the photo. Oh, hang on a second.
How will they know we're Brills?
There's a resemblance.
Would you like the granddaughter or the son closest? The honor.
And I certainly have no prepared remarks, but I just want to really say on behalf of all the Brills,
thank you so much to the wonderful speaker and to the Academy and the AIAA for sponsoring this and keeping my mom's legacy alive. I know she would just be thrilled and so humbled and honored by such great.
Appreciate it. Yeah. So, Penny, once again, that was wonderful. Really appreciate it. And thanks to everyone who joined us here. The lecture has been recorded, in case you didn't notice. And within a week or two, it'll be on both the AIAA and the NAE websites. So you can review it and really dig into the details of GNSS. I know I'll be doing that. And of course, we'll be awarding the next awardee in this lecture series in 2 years. So in October of 2026. For those of you that are physically here with us today, you're invited to a reception in the East Room, right through those doors, where we can continue the discussion. Thank you again for participating. I appreciate it.